You're probably familiar with the problem of classification, where you have a bunch of observations and you need to attach labels to them. So, for example, a bunch of images, and you say this is an image of a cat, this is a dog, this is a shoe, and so on. Or maybe you have a bunch of customers and you're trying to classify them as this is a high spending customer, or this is a low spending customer, or whatever. Sometimes when you're classifying, you don't actually know what are these target labels. You really don't know what the groups are that you're trying to assign the different observations to. And that's what cluster analysis is useful for. It's a so-called unsupervised algorithm in the sense that it tries to assign groups or find groups for observations when you don't know what they might be. So it tries to look for patterns or similarities. And cluster analysis is going to be the topic for our last 4 lectures of the class. And we're going to cover this topic in a way that's kind of similar to the way you would if you were just hunting around and trying to learn about it by yourself. We're going to do a bunch of code, kind of explorative things to see kind of an overview, just sort of looking at some of the tools that are available. And then after that, we're going to dig into the technical details of how those tools work and what makes them different and so on. In today's lecture, we're going to look at a bunch of tree diagram methods for something called hierarchical methods. But those words aren't super important right now. We're just going to sort of get the feel for the subject and go into the technical details in later lectures. Okay, let's get started. The topic for this and the next 3 lectures, so 4 lectures altogether, is called cluster analysis. Clustering as a topic is pretty broad, so this topic is broad. And you could even say it sort of is resistant to definition. There might be various different interpretations, people who disagree on what qualifies as clustering or not, but that's certainly not really particularly new to many of the things that we've covered, and to multivariate analysis as a whole, really. But I just want to kind of describe what I think are kind of the key points or the key aims of the topic. So these are just the aims. After this little chat here, we're going to go and do a bunch of work in code. So we'll be there in a moment. So the one main aim is to try to arrange your data into meaningful groups that get called clusters. Arrange data or observations into meaningful groups. And they're sometimes not called groups, but instead called clusters or classes. Just different words for the same things. And so here, when I say observations, of course, what I mean are like the rows of your X matrix. So you want to somehow find some way to group those rows into certain types. You want to kind of classify them. It's really, in a way, the defining feature for me is that this is sort of a mechanism for reducing the number of observations, which is new to us in this module. So, mechanism for reducing. A lot of our work is about, in multivariate analysis, is about reducing kind of the size of the data that you have to deal with, to kind of distill out of it the key or important aspects and brush away the parts that are somehow not as important. So that's kind of a lot of what we've been doing. And this is a different kind of approach to this, where what you're doing is you're reducing the number of observations rather than the number of features or parameters. Right, so the data matrix X, which has all the observations in each row, So that's got n rows and p columns for us. So that's the notation we've been using. We also talk about the dissimilarity or distance matrix, and that, if you have n different observations, is n by n. And so as you've seen, like principal component analysis, which we spent a lot of time on, and multidimensional scaling, which I think we just, what did we have, 4 lectures on maybe, I think just recently. Those both reduce P, or they can, at least. They reduce the number of features or parameters. They can be seen as ways of doing that. And clustering reduces N, or can be seen that way. Cluster analysis. I should put quotes around these things because it's a little bit of a crude description to say that that's all those things are for, reducing those numbers. That's not quite right. But that's in essence like what are their kind of powers in my crude opinion. And so we are not going to look at clustering in its entirety. There's quite a lot of pieces of it that we won't cover. But we are going to study sort of 2 broad types. So we'll study in this class, so study 2 types of clustering in our module, and so in MT 5758. And they are the following. They get the following names. So the first one is called hierarchical methods. And we'll spend more time on those, roughly 2 lectures. And the second one that we'll spend a little bit of time on is called partitioning methods. So those are the 2 types of clustering analyses that we'll go through in this module. And today we're going to do a sort of an overview of the first one. All right, so today we're just going to do the following. All right, we're going to explore hierarchical methods. And I really want to emphasize explore because we're not going to define everything that we see. We're going to, like, for example, we'll run some routines and I'll change some parameters and we'll see things change and we won't know exactly why. And we'll talk about that in the remaining lectures. But so today it really is about exploring, so we won't define everything today. But instead we'll revisit. So today we're going to look at a data set that is a survey, a questionnaire, and I'm pretty sure that this was a questionnaire given to St. Andrews students, possibly even in this module, but I'm not sure. This was before my time. And so it was a questionnaire that was given to people, and it has 32 questions on it. Some of them, the first 3, so these are all the questions. So this is basically the questionnaire that you see here. The first 3 questions we won't really deal with. They're asking gender and age and distance from wherever it was you were born to St. Andrews. And then the remaining questions, which are, I think, 31 of them or something like that after that. Well, we'll see. 28? I don't know, whatever. The remaining questions are all the kind of questions that you've probably seen on surveys before, which say something like, answer the following on a scale between such and so and such and so. And so this time it's on a scale of 1 to 10. And all of the questions are of the form, how much do you like blank? And the responders were meant to give a number of 1 if they really like the thing a lot, and 10 if they really dislike it or don't like it at all. And so these are all kind of like ways to spend your time. So going to cinema, going to theater, all these things. There's a lot of things on here that we can't do, that we've not been able to do for a while because of the COVID restrictions. Um, but there are things on here you could still do, cycling, at least depending on where you are, running and so on. Anyways, but so there's all these different activities on here. I like this doing nothing. That's a nice one. But yeah, so there's all these different activities, and the people were asked for all these different things, tell us whether or not you like these things and how much, right? And now this is exactly the kind of data set where the the observations are difficult to kind of deal with in a way because what one person's 5 might be another person's 7, or so it's hard to know kind of what's going on here. And so we would focus probably on the dissimilarity matrix here rather than on the actual observations. So like if one person is sort of liking everything a lot, we'd notice the difference between that and somebody who dislikes everything a lot. Um, okay, but so anyway, so the first thing we'll do is we'll read in all the responses. There's 31 responses, so that's another indication that this was a class, 31 students. Our class has 30, I think, so it's quite close. But anyways, we'll read this in, and the data set, I'll put this on Moodle, you can get it, and you can also get a description where I got the questions and stuff like that. And it's small enough that I can show it. So there's 32 questions and 31 responders. And we're going to throw out the first 3 columns. You can see all the usual sort of data issues here, like these are supposed to be distances, and some people put NA. And I don't know if I don't think there's anything problematic in these hidden columns, things too big to show on the screen. Or is it? Yeah, we miss about 12 columns here that you don't see. But I don't believe there's anything in there that's a problem. And we're going to focus on columns 4 and higher, which are the ranking 1 to 10 questions. So we're not going to look at the other stuff. Although you could sometimes do that afterwards. But okay, so we're going to focus on questions 4 to 34. And they should all be integers. And so let's just name that thing main data. And again, we're going to focus on hierarchical clustering today. And the routine that we use to do that in R, or that we will use to do it in R, is called hclust. And of course, you could run the help file here to take a look at it, and I'll just do it really quickly. And you can see the number of things that it gets as inputs. So it gets D, which is a distance matrix, method, which is a parameter we'll play with today, but that we won't really explain in details, but you'll sort of see something interesting is going on. And then there's this other parameter here, which we won't use. So this is the help file. You always should, of course, be aware of kind of roughly what's in here and so on. And I will close it now, and we'll start playing around with things. So the first thing we're going to do is take that data set, which was, as I said, all kind of from different people, and so the observations might not be as interesting as the dissimilarities or the distances. So the first thing we're going to do is create a distance matrix out of that. And we're going to use a Euclidean distance here, which maybe is not really such a good choice here, because all those numbers are integers, and so it might make more sense to use a Manhattan distance, which we will do near the end. But yeah, so we'll make a Euclidean distance matrix first. And I want to just remind you, since we're really in kind of an exploratory stage here, and we're just kind of seeing what this algorithm does, or what R can do with this clustering stuff. I want to remind you that when we feed the hclust routine a distance matrix, that it's not just a matrix, right? It's not just the symmetric matrix of distances, although it is that. It also includes information about how the distances were computed. And so that's kind of important to be aware of when you're just trying to understand what is something doing with this object that you give it. So I just wanted to remind you of that. So we'll go ahead and run our first clustering analysis on this, and we're going to use the so-called single linkage scheme. And again, we'll revisit this later to try to understand what that actually means. We'll kind of give you a rough picture today of what it could mean, or what it is, what kind of things it might be controlling. But we won't actually see exactly what it's doing. But so let's do this, and then we'll take a look at the response. We'll just print the output. And the output is a few different things. So first there's just the line that we used to call the thing. And then there's the linkage scheme that we used. There's the type of distance metric or distance measure that was used by our matrix that we gave to it. And then there's the number of rows, or rather n in our case, right? There's 31 different observations. And the primary way that we're going to look at the results of clustering is through a series of diagrams that you could call tree diagrams. But they are, I think, maybe more often called dendrograms, which is literally, it means tree diagram in ancient Greek, I believe. Which I always think, you should sort of think of this as a red flag when somebody's taking something simple, a simple name, and putting it into an ancient language that isn't really used to try to make it sound fancier. I always think that's a worrisome sign. In fact, the notes, the author of the notes for our class, that you can see I think it's two people this semester, Len Thomas and Valentin Popov, for this chapter. You can see they're kind of skeptical of the topic as a whole. I think at some point they say, the first rule to remember when dealing with clustering is to distrust results, or something like that. But so maybe they also think there are some red flags. But anyway, so let's see what this looks like. We use the plot command, and you'll get a dendrogram, which, by the way, I often slip and call dendogram, but I believe the right name is dendrogram. And so here's what you get. So this kind of a diagram here, and you'll have seen a lot of these if you flip through the notes. And we'll discuss what this means for like the next 5 minutes or so. We're going to kind of talk about what this is, what's going on here. But for now, I just want you to see that this is the kind of diagram you can get if you just plot the output of the clustering routine. Okay. So now let's talk about what is going on in the algorithm and what is being represented with this tree diagram. So I've written this long blurb here, kind of to save me from a lot of bad handwriting of kind of words in the whiteboard thing, but we can go through them here. So the first thing to kind of know about this is that the numbers that you see here along the bottoms of these little sticks or these little branches, these refer to the observation number, right? So there should be 31. Is that right? Yeah, there are 31 observations, or maybe 30. We'll see why that makes sense in a minute. But so these are the different observation numbers. And, oh yeah, there's 31. So that's what those numbers are there. And what's happening here is that they are all getting kind of like merged together. So there's some kind of path by which you link up all these different things. And we'll talk about how those choices are made and what those links actually mean. Okay, so now again, the algorithm, it does not actually have the data matrix, right? So it only has the dissimilarity matrix. It doesn't make any use of the observations directly. It only works with the distances. And so the first thing is we're going to name each observation or row of the data matrix that we don't actually see in the algorithm. Each of those observations is going to be called a cluster. And initially, the distance between the clusters is given by the distance in the distance matrix that you initially provide the algorithm. And what happens is we go through a series of iterations, and at each iteration, which is represented on the diagram here by height, it's unfortunate this doesn't go down lower. You should be able to see like 0 or something like that. I don't know why it starts at 10. But there's some kind of iteration number here. And that's telling you like at which step you are in the process. And you can go as high as n here. So it should go up to about Doesn't go quite up to 30. But anyways, so this is what this iteration translates to, is where you are vertically on the diagram. And the very first thing, what you do at each iteration is the following things. So you find the two, the smallest distance in your distance matrix. I should put this here. And you merge the two most similar observations. And merge means, so first of all, most similar means the smallest dissimilarity, or the smallest distance, or the greatest similarity if you want. And merge means kind of two things. So first it means on the diagram you show a link between the two things. And so you can see that up here. So like here is the merger of observation 13 and 4 is what's happening right here. And then whatever that thing became then gets merged with observation 5 and so on. So the first thing you do is you draw on the diagram then a little link merging these two objects. But more importantly, what you're doing to the data itself, or to the distance matrix, is you're reducing the number of its elements. So you're taking, so if you merge two objects, two observations, then for every pair of observations, right, there's two elements in the distance matrix, which is symmetric. So there's distance from one to the other, and then from the other back to the one. So those are the two different distances that are in there. And in our case, that's a symmetric thing. And so every time you merge two things, you reduce the size of the number of observations. So like let's say you had 30, is it 30 we had? 31 observations, and you take one out and somehow merge it with the other. You now have 30 observations. So you went from having a 31 by 31 distance matrix to a 30 by 30 distance matrix. So every time you do a merger, you change the distance matrix and you make it a little smaller, right? And then there's some kind of more complicated definition of what are you actually doing to make this merger? Like, are we just throwing out one of them, or averaging something? And then we'll talk about that. That's the kind of thing where the single linkage choice plays a role in what exactly are we actually doing at that point. But anyhow, so the idea of the algorithm is you keep doing this, you keep iterating and doing this until the distance matrix is so small that it's just a single number. And at that point it's 0, because it's the distance from one object to itself. Yeah, and so that's the rough idea of what's going on here. This just says, if you take a look at this last line, just says, if you take a look up above, you'll see the first merger in our case here is between observations 29 and 30. And so you can go over here and so you can take a look at that. So that's the lowest things on the plot here is 29 and 30. Yeah, so that's the merger of those two things. And so those then become one thing, one observation. So you then have n equals 30 after that. You keep the same labels on the other things. This one, you don't really have a name for it, but you do see that the next step along the process is that it gets merged with observation 21. And so this cluster then of these three after that gets merged with observation 27. And so this is now a bigger cluster of it used to be 4 observations, so it's now one cluster. And so we're sort of slowly swallowing these things up into clusters. Okay. Now, so again, it starts off with the thing that has the lowest distance, and so we can verify that just sort of for fun. So we'll look at the smallest value of the distance matrix. And that number shouldn't surprise you really if you think about it, because the distance matrix, right, it's diagonal, all the diagonal elements are 0. Those are the distances from an observation to itself. So of course, that's not going to be an interesting number. So we'll look at the minimum value of the distances that are bigger than 0. And it's 10 point something. And then we'll see what are those. So we'll check, show me where the distances are equal to that thing. And so sure enough, there's 2 values with this. And then we'll verify that that's distance 29, 30. It's also distance 30, 29. And so that's just checking that indeed the first merger on that diagram was the merger between things that had the smallest distance. Okay, and so now we'll try it with a different distance matrix, probably one that maybe makes a little more sense in this case. We'll use the Manhattan distance. I don't know if I've ever mentioned this, but that's the same as the Minkowski distance measure with the power parameter p set to 1. Anyhow, so we'll do that and we'll make a new diagram. And this in principle should be pretty different because it's using a totally different distance measure. Oh, sorry, we're not going to show it right away, but we'll just see the output. And again, you see, I just want to draw your attention to the fact that the algorithm knows that the Manhattan distance was being used here. Okay, and so we'll plot the tree diagram or the dendrogram here. And it does look pretty different. So like this 1 and 11 is way off over here being merged with this really quite large cluster. And I don't know if you see that over here. Certainly you don't. Like 11 is here getting merged with everything that was below it, but not with 1. You don't see it getting merged with 1 in some special way. 1 actually is added later. But yeah, so the diagram is certainly quite different, which is not a really big surprise since we used a different distance measure. Okay, and now we're going to do a bunch more just to kind of get a feeling for how they change when we change different parameters. And I'm just each one of them I'm just going to write in a single line here. So the first one is this is how to run all this in one line using the same single linkage parameter that we used. So this is our first dendrogram shown again. One thing changes here. The label that's shown down here tells you a little bit more information. It tells you exactly what it was that it was applying. So you see that it's using the distance matrix based on some data matrix. Whereas before, I think all you get is you're told that it's handling the object Euclidean, d-Euclidean. So you get a little bit more information shown on the plot, but that's not really that interesting. Okay, and so let's take a look at some of the other diagrams. So we'll look at the so-called complete linkage. And that's quite a different picture. See, this one has this sort of weird chain that goes on here. And this one looks quite a bit different, or maybe it isn't. So you have to think about kind of what's going on here. There's a lot to do with sort of the geometry of the diagram that sort of helps you or doesn't help you to see certain effects. And so at the end of this lecture, we'll look at a few other kind of alternative dendrograms that might be more helpful at displaying kind of what it is you've done. So we'll look at 2 other linkage schemes. The one called average. It looks like this. It looks different than this one. Both of them are all of them seem to be starting with 29 and 30. 29 and 30 here. Oh, and you might, so we should do this though. Look, so if you look at this, all of them also seem to end with observation 20. So observation 20 seems to have been sort of the furthest from all of these things. And so we should be able, let's take a look. We'll go back to the matrix, the observation matrix or the data matrix and see what is going on. So we're way back up to the top here. So what is going on at observation 20? So we actually have to count these. I don't think I have an index there. This guy, this is observation 20. And so I think if you look at this, you should be able to see there is something unusual about this observation, or something that might make it more sort of dissimilar to all the others. This responder has said 10 or 9 to almost everything. Well, at least to all the columns that we can see. And I don't know if you remember, but that means they dislike everything. I think let's double check, but that's what that says. Yeah, that means they really don't like anything. So that person, maybe they don't like the person who was leading this class, or maybe they just don't like everything. I don't know. Anyways, but that's a very singular kind of a response, and so that's why this one individually this one observation 20 kind of was the last to merge with these other clusters. These, so the early things like 29 and 30, I think those were the two that got merged at the start. They might have a lot of things in common, like maybe they said really high numbers for all the cooking activities or for all the music activities or something like that. And so you get the idea that you're kind of classifying these responders into different groups, people who really like music, say, or people who really like the active activities like swimming or cycling and stuff like that. And so that's kind of the power of the clustering analysis. Okay, so let's go back down here and see the last couple of dendrograms. And then we'll see some alternative style ones. Oh, we've only got one more to show. This one has a very mysterious sounding name, Ward D2. And it does also look a little bit different. It also, 20 is nearly the last thing to get merged here. But yeah, anyways, so these are the different examples of the types of hierarchical clustering that we'll be looking at. But I want to show you, so one last thing before I go, I want to show you some kind of alternative to these sorts of dendrograms. And so to do that, I want to reference the Zelterman textbook, and I think you might want to look at it. I think it's even on the cover of the textbook is an alternative dendrogram. But so we'll go over to it right now. This is early on in the clustering chapter. These are some dendrogram type things from there. And so this one, I think these are American baseball teams. I think that's what these are. And these are different types of diagrams for the same data sets. I don't know what this data set is about. I don't know what it's saying about these teams. But I want to draw your attention to kind of the different shapes and stuff here. So one thing that's different straight away from what we've been seeing is that all of the observation labels are like smooshed down onto one axis here, leveled out. And to find out where they got merged or whatnot, you have to kind of go up the path to see. So rather than chopping this line down here and labeling New York Mets right there, instead they push all the names down to the bottom. This one is quite similar, except it's all of the mergers happen sort of at an angle instead of at right angles. And there might be some utility to doing that, or maybe not. So there's a lot of things you can try here. There's some more, these are sort of like rounded things. So this one is called unrooted tree. This is maybe my favorite. It really draws attention to the fact that this grouping here is off to the side like this, and this grouping here is off to the side like this. And I think you can sort of see that here. But to me, this is a clearer representation of that. And then there's another version over here this is kind of like purely a rounded version of the plain dendrogram. Looks like this. And as I said, you can then color these things, or you can then add in information with using the features that we didn't actually use. So like in our case, we had gender and we had distance from St. Andrews and stuff like that. Here they have something. This color tells you some kind of sports term, something about where these teams play or something like that. And they've colored things accordingly. So that's just a quick sort of overview and exploration of hierarchical methods in cluster analysis, or hierarchical cluster analysis methods, however you want to say it. We're going to do a little bit more of this kind of exploratory stuff in the next lecture, which will be a little bit of a short one, and then we'll cover some technical details after that one. See you then.